is part of soil fertility management courses, as well as the opening of the art semester 2022. And for that, today we are inviting a remarkable professor from the overseas. But first of all, I would like to welcome the Honorable, the Vice Dean of Academic Affairs, Dr. Sujarwo SPMB, as the representative from the Dean. And then the Director of Postgraduate Program, Faculty of Agriculture, Professor Dr. Insinyur Kuswanto MP. Thank you very much. And the Graduate Program Secretary, Dr. Insinyur Cici Udayana MSI. And the Head of Soil Department Study Program, Mr. Syahrul Kurniawan, SPMP PhD. Thank you very much for coming. And welcome to all the faculty agriculture professors, lecturers, and students who are coming to today's guest lecture. Thank you very much for coming today. And of course, I would like to give my warmest welcome to the honorable guest lecturer today, Prof. Chris Anderson from Massey University, New Zealand. How are you? Do you have a good day here? Thank you very much. All right. So I hope you have a good day in Malangan Faculty of Agriculture. Okay. He is a professor in environmental science and a director of agricultural landscape. And today he will talk about pest management for improving soil fertility and reducing environmental pollutions. And I will also welcome to the moderator today, Dr. Reni Ustiati from the Soil Department, Faculty of Agriculture, Universitas Brawijaya. All right, to start the guest lecture today, I would like to inform the schedule or the rundown for today. The first is greeting from the head of graduate program, Professor Dr. Insinyur Kuswanto MP, and followed by the opening from the representative of the dean, uh, Bapak Dr. Jarwo. And then we go to the main session with Prof. Chris Anderson, and we will have Q&A and discussion session that will be led by Dr. Reni Ustiati. And during the lecture, the student need to summarize or take notes on Prof. Chris' lecture and submit it later. And the task detail will be explained by the moderator. And the last agenda is hand over the souvenir and taking photograph together for today's documentation. Well, to take the advantage of time, I would like to jump into the main agenda, the lecture. Okay. And then I would like to start by give the time to the Director of Postgraduate, Professor Dr. Insinyur Kuswanto, to give the opening remarks.
Okay, thank you very much to Vida and Honorable Prof. Chris Anderson from Massey University. Thank you very much for your coming. And then thank you very much, Mr. Dean, Initial Vice Dean for Academic Affairs, Dr. Sujarwo. Thank you very much, of Director of Soil Department. Thank you very much, Prof. Chu, Koniatun, and then all of students, Magister program, maybe some student in here, PhD program. Thank you very much for your coming all. And it is a good time for a student, especially for Magister program, to improve your experience to discuss or maybe some information from overseas. In here, we have special guest, Professor Chris Anderson from Massey University. And I have known Prof. Chris maybe since 2019, maybe, while you spent in guest house, and then I came there to discuss about how to make Agrivita become international journal. Maybe you remember. It is first time I know Prof. Chris Anderson. And I tell you now, Agrivita have index in Scopus in 2013, maybe 19, since 19 ago. And today I say thank you very much for committee and Soil Department program, because this meeting, selamat datang. Monggo Prof. Eko, terima kasih. Thank you very much, Prof. Eko. And then Bu Dewi, thank you very much. Okay, I continue my speech. And okay, today the good meeting for opening the lecturing in this semester for master program or PhD program here. I think it is the good process like this last year and 2 years ago. We always held the lecturer in area of semester. And I think it is enough for me. And thank you very much for Bumida. I back to moderator.
Professor Dr. Insinyur Kuswanto for the greetings. And then we step on the following agenda, the opening from the Vice Dean of Academic Affairs, Dr. Sujarwo. The time is yours.
Okay, Bismillahirrahmanirrahim. Hope I didn't, I will not take longer. So Prof. Chris will share quickly after me. So I just want to give a warm greeting from Dean of Agriculture Faculty for coming in our faculty, and Prof. Chris Anderson. We're really glad having you because such right time we now in Indonesia having a big problem about really using massively chemical fertilizers, and how to manage land resources become harder and harder because just farmers really depend on chemical fertilizers, and pH of the soil become lower and lower. So hopefully that we have a kind of good treatment for agricultural resources, considering environment. And today, guest lecture by Prof. Chris Anderson is kind of opportunity for us for having a good understanding about how to manage our resources to become sustainable, right? Hopefully that we will get more advantage in having Prof. Chris right now. So, our all respect to Prof. Cho, Prof. Kus, Director of Graduate Program, Prof. Eko, and Bu Dewi. Thank you very much for joining with us in these guest lectures. And also, Prof. Yayu, I just met in the second floor, Bu Suhartini from agriculture socioeconomics, but concerns about the environment. So hopefully that we will get benefit in sharing in the session. And also all the students, all graduate students, Bu Cici, thank you for organize this meeting, this event. Thank you very much, and hopefully that it is the progress of how to manage resources get better and better, applicable for the farmers. It's not only for writing in the paper, but have to be real knowledge to be implemented by the farmers. So hopefully that research that we have done, or we will do that research related to the environment, related to how to manage the resources, become real in the society, real in the agriculture development. So, Prof. Chris Anderson, thank you very much again for coming with us, sharing the best practices how to manage soil fertility and reducing the negative environment impact. Hopefully that this will be your research interest, and we make more collaboration with Malaysia University, New Zealand. Sorry for pronunciation. Again, we really appreciate Prof. Kus, Director of Graduate School, Faculty of Agriculture conducting this event, guest lectures like that. It's not only for opening the session of the semester, but also probably have continue doing this for getting more and more knowledge about the advanced knowledge right now, conducted by the expertise like Prof. Chris Anderson, so we can develop more communication internationally. We can share internationally what we have done with the expertise outside there. So thank you very much again. And with Bismillahirrahmanirrahim, we open the guest lecture with Prof. Chris Anderson for today's event. Thank you very much.
Thank you very much for the opening remarks, Sujarwo, SPMP. And before we start the lecture itself, it would be better if we take a photograph because we still have a complete personal years. Okay, so I would like to invite the lecturers from the soil department or who are invited today or who are coming today to take a photos in front together. All right. Kita berdiri. Everyone, all right, all right. Could you please stand up? And then I would like to invite the lecturers, Bapak Ibu monggo, silakan menuju ke depan untuk foto dulu, mau lengkap. Yes, yes. Oke, monggo. Join the lectures. Ibu, Bu, monggo, 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 monggo. Bu, monggo, monggo.
Pasti Pak Jago saya ajak pertimbangan. Data ini benar tak Pak?
Monggo. Monggo Bu Cici, Bu Yayu, Bu Yulia, foto dulu mumpung ada lengkap.
Kuat dihadapkan dengan ranah hukum.
Much, Bapak Ibu, all of you, thank you very much for coming today. Thank you, Ibu. Thank you. Bu, siap-siap, Bu. Siap-siap. So that's the opening for today's agenda. And to take the extended of time, I would like to jump into the main agenda. But beforehand, I would like to introduce our moderator today by showing you her CV. For the operators, could you show Ibu Dr. Reni Ustiati CV? Could you help me to show her CV? All right. All right, thank you very much. Okay, so our moderator today is Ibu Dr. Reni Ustiati. She is a lecturer in the Soil Department, the Faculty of Agriculture, Universitas Brawijaya. She graduated from here too, actually. and she had a research grant in 2020 on endophytic bacteria isolations. Perhaps it will be your expertise, perhaps. So here is Dr. Reni, and without any further ado, I would like to give the time to Dr. Reni as moderator to lead today's discussion. Dr. Reni, the time is yours.
Thank you, Bu Hafida. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon, ladies and gentlemen. Welcome to guest lecture for the beginning of new semester to 2022-2023. The Honorable Prof. Kurniatun Haria, Prof. Eko Handayanto, the head of Soil Department, Pak Budi, Pak Syahrul, the head of Soil and Water Management Study Program, the Honorable Bu Suhartini and Bu Dewi. My name is Reni Ustiati. I am a moderator for today's guest lecture. But actually, you don't need a moderator for a lecture. If you have any question, please ask your question during the discussion session. Please feel free to ask in Bahasa Indonesia. I'm happy to help you all of students that joining us online or offline when you have question. And let me inform you further about today's guest lecture. The guest lecture is Professor Christopher Anderson. Please, could you please show his curriculum vitae? Yeah. He is professor in environmental science, group leader environmental sciences in Massey University, New Zealand, chief scientist Croesus Project Limited. Prof. Chris holds business and academic position in several countries. He works at the interface of science, technology, community development, and business to promote sustainable development in mining and agricultural communities. In New Zealand, he holds the position of professor in environmental science at Massey University and is the group leader environmental sciences at the School of Agriculture and Environment. He is the director of Massey Farm Landscape Research Center, which supports the sustainable of New Zealand's primary production sector, and the chief scientist of the New Zealand environmental consultancy company named Croesus Projects Limited. As a result of his international activities worldwide, he holds the position of adjunct professor at the Institute of Geochemistry of the Chinese Academy of Sciences and other prestigious universities worldwide. He leads an active and global research group investigating the interaction of trace elements and contaminants with the environment. His project on trace metal contamination in soil, organic pollutants such as dioxin, essential micronutrients, and major nutrients in farm system underpin his H index Scopus on August 2022 of 30. Please give a round of applause. On today's guest lecture, we will discuss about integrated soil fertility management. We will have 60 minutes for lecture and 30 minutes for discussion. So students, please prepare all your question and ask your question on the discussion session. Please, Professor Christopher Anderson, time is yours. Yeah. He wants to move around because we have prepared for the whiteboard also. I will help you.
Okay. Thank you very much for that introduction. It is a great pleasure to be back here in Malang. It is a great honor to be able to open this semester. And I can say that Universitas Brawijaya and Malang have a soft spot in my heart, because this with Pak Eko was where I started my research activities in Indonesia. So it feels great that my first travel since COVID is back to Malang. So thank you very much, Reni, for your kind introduction. And thank you for being here today. I've got quite a daunting topic to talk about. So the idea of talking about integrated sustainable nutrient management is very broad. So what I thought I would do was go through some principles. So think about some of the basics that we need to consider. And then I'm going to apply that to rice, to paddy rice, because I realize that that is quite a challenge environmentally for Southeast Asia as well as Indonesia. Now, I've been told that I can set some questions. So maybe I have got a concept that I would like you to think about. So through this lecture, and this will be good for the master's and PhD students, think about why nitrate leaches, because we talk about the environmental problems of nitrate being due to leaching out of the soil profile. So let's think about why that is. It's use soil chemistry to explain it. But I also want you to think about why phosphate will be subject to erosion. It will run off. Because nitrate's NO3 minus. Phosphate is H2PO4 minus. They're very similar chemically. And I'm hoping that many of you already know why they behave differently, but I'm hoping to be able to help you explain that perhaps more clearly, because you all as environmental professionals, and I say that for soil science, for plant pathology, it is very important that you can communicate with farmers, with industry, and with communities. So I want to think about some good science that you can use to support your communication, your research into the future. Now, just as a bit of a starting introduction, I am from Massey University. We are very fortunate in New Zealand, and Reni would be able to appreciate this, because the last time I saw Reni was just as New Zealand locked down for COVID. So Reni had the last flight out of New Zealand before the borders shut. I scrambled to get her a ticket on Emirates to Denpasar. The next day, the country shut. So while she now thinks it would have been nice if she was still there, I'm pretty sure she was happy to get home. So we are focused on agriculture. Pak Eko has been there as well. So we are very much focused on agriculture. We have been an agricultural college since 1928. And then we were a university from the 1960s. We have 32,000 students in total, not as many as UB, but we have campuses in Palmerston North, where I'm from, but also in Auckland, our biggest city, and in Wellington. And we have a lot of students that study via distance or online learning. So my campus in Palmerston North, where we do agriculture, only has about 7,000 students. So very small compared to Universitas Brawijaya. We have a strength in agriculture. We have a strength in PhD programs. Pre-COVID, those numbers are. We had 400 PhD students in agriculture at any one time. We are fortunate to have 2,000 hectares of farms. So one of the strengths to what we can do is study farm systems. I'm very proud of our QS ranking in agriculture and forestry. We are QS ranked 52nd in the world for agriculture and forestry. And I am excited to be thinking over the next couple of days about how we can re-engage with UBI and strengthen the partnership that we've had for 14 years since Paeko first invited me to come here. But preceding that, Massey and UBI had strong relationships in animal science. So the relationship between our two universities goes back into the 1980s. And I think it would be great to see us redevelop this. We have our only vet school in New Zealand, so another strength is our veterinary medicine and our veterinary science. And we're part of the Global Food Safety Partnership and the Global Alliance on Food Security Research. So talking about sustainable agriculture in this context is very important. So this is what we're going to do, and I'm going to keep an eye on time. I'm just going to have my phone there so I can check time periodically. I want to go through some science. I want to talk about dissolved ions. We're going to talk about the soil because this is going to be focused on the soil. We'll talk about the reactive parts of the soil. I want to talk about charge. It's a very important concept to sustainable nutrient management, and especially those of you that are from plant science and plant pathology, understanding what makes the soil work is really important. So we'll talk about charge, because that tells us how how soil holds on to nutrients, which gets to the topic of our lecture, the implications for nutrient management, and then how we apply that nutrient management to, I'm going to talk about rice. Okay, so I want to step you through some science, some of the fundamentals, and then that will provide a framework for the implications for rice production. So remember why nitrate leaches, but why phosphate will be subject to erosion. I want to tie our work back to understanding why. Why does nitrate leach, but why does phosphate run off? Okay, so number one, let's start with dissolved ions. And I'm going to do this fairly quickly. If I was here for a longer period of time, I could go much more slowly and we would explore this in much more detail, but I want to give you an overview. So we're going to focus in on some of the key points. And the first principle is that our work as soil scientists, and I'm a soil chemist, our work as soil scientists, soil chemists, is to look at the soil solution. Okay, the water in the pores. It is the lifeblood of soil. If a nutrient is not in soil solution, then it's not of any interest or relevance to any of us. Plants take up those nutrients. Oh, hang on, I'll just go back there. Plants take up those nutrients. That's right, I don't need the pointer. From soil solution. So you can see that in that little model of some soil particles, I've got a green plant root. What's happening is that we have ions dissolved in soil solution. There's cations that are positively charged, and there are anions that are negatively charged. Now, if they're not in soil solution, plants cannot take them up. And that's a very simple principle, but we must remember it. If we are understanding nutrient management, we need to be thinking about what is dissolved and in soil solution. Now, our chemistry in soils is the reaction between that water, that soil solution, and the soil surfaces. And you can see that those soil surfaces have lots of color. We've got a yellow soil particle. The green indicates organic matter that coats soil particles. There is some orange, that's an iron oxide coating. So the soil is complex, those surfaces are complex, and as soil scientists and as nutrient managers, we need to be thinking about that interaction between the water and the surface. So this is where it all happens. It happens in soil solution. Now, these are numbers that would indicate the sorts of concentration ranges that we find in New Zealand for ions in soil solution. Now, you'll note I've listed the elements. And the first thing you need to do when you start looking at elements is think, what is the dissolved ion that plants take up? Nitrogen. Plants take up ammonium ions, or they take up nitrate ions. And you can see that the sort of concentration range that we find in New Zealand soils is on that right-hand column. Phosphorus. Okay, once we're interested in phosphorus, if we're a farmer, we're applying phosphorus. We then need to think about dihydrogen phosphate, H2PO4. It's not PO4 minus. It's not H3PO4 as in phosphoric acid. The form, and as postgraduate students, this is what you need to start to be understanding, the form of phosphorus that's stable in our environment, that exists in soil solution, is that one there, H2PO4 minus. But it's got a very low concentration. Okay, so there's the first sort of hint. It's not soluble, very low concentration, and we're going to explore that as we go through. The cations are easier. Calcium is calcium 2+ ions. There's lots of it. Magnesium, magnesium 2+. We've got potassium and sodium. So there was a range, but these are the nutrients we're interested in. And we need to be able to diagnose what's happening to make sense of our nutrient management. Okay, so there we go. There's the first point, soil solution. We're now focusing on not the element, but the nutrient in the soil solution that is going to be taken up by plants. So what do we do next? We think about what those nutrients are interacting with. Now, I notice in your 3-in-1 program, you have some lectures around the mineral fraction of soil. Now, the mineral fraction of soil really describes everything that's not organic. Now we're thinking about what that soil solution is reacting with, what that surfaces that we get reactions on. And we use these words to describe those mineral fractions, and they're based on size. Now we talk about gravel. So gravel is a technical term that we use to describe particles in soil that have a diameter greater than 2 millimeters. It's what gravel means. It's a size. Sand particles in a soil between 60 and 2,000 micrometers. So smaller, but we can still see them. Silt, 2 to 60 micrometers. Then we get down into clay. Now, when we say the word clay, what we basically mean is tiny. And that's what we need to think. When you see the word clay, in the context of soil science, you need to think small. And in this case, it's a size of a particle that's less than 2 micrometers. And then below that, we get gels. They're amorphous materials. They have no crystalline structure on X-ray diffraction. And so they're very hard to describe from a physical perspective. Now, you have a lot of gels in your soils here in Indonesia. They form from volcanic ash. The mineral allophane is an example of a gel. It's tiny, and it performs a very unique function in our soil. Now, that size is really important, and this is a figure that I use when I'm teaching my undergraduates in New Zealand to try and really think about how different these physical components in the soil are. Oh, we've gone a bit far there. There is a sand particle. All right, so what we've done is we've tried to represent the difference in size between sand, silt, and clay. So if we were to draw a sand particle and we were to relate silt and clay to that scale, there's what the silt particle would look like. And then the clay particle has been blown up by 10 times. So the clay particle is very, very small. Now, the sand and the silt is important. It's important because it provides structure. It provides porosity. It provides drainage. But it's not particularly interesting that get smaller. Now, what happens is that we can introduce another word here, okay? Pedogenesis. Now, that's a word I'm hoping you're all familiar with, but pedogenesis is the word that we use to describe the formation of soil. And pedogenesis is a function of climate, vegetation, and time. What happens is that we have rocks. Here you've got volcanic rocks. Those volcanic rocks will break down. They weather, rain, cold, plants, wind. What happens is that they will cause fractures, they cause breaks in the rock, and the rock particles get smaller and smaller. They turn into gravels. The gravels get smaller, they turn into sand, they turn into silt, they turn into clay. Now, what happens is that as we break down, as these rocks break down, their mineral components, the nutrients, the calcium, any phosphorus, the potassium is released into soil solution. And once it's released into soil solution, we can start to think about what can happen to those nutrients. So in the middle there, I've got dissolved ions. Now remember, that's our soil solution. And it's about this point, what I do when I'm teaching my undergraduates is I get them to say, right, what happens to those dissolved ions in soil solution? And I can tell you that one of three things happens. Top one there, dissolved ions in soil solution that have been released through pedogenesis. They can be taken up by plants. So they go up into the plant. That's what we want. As sustainable nutrient managers, we want those nutrients to be taken up into plants. What we don't want is for them to leach. We lose them. That is bad news for our bank balance. And that is bad news for the environment. So we don't want them to leach. So instead, we want to understand how they can react with the soil. And what we've got there is we've got the indication of reaction. Notice we've got equilibrium lines. It's a reaction. It goes backwards and forwards. I'm not going to explain cation exchange capacity in detail, but that's a major part of what happens. But those dissolved ions can form minerals, secondary minerals. They can be absorbed onto the clays that we've formed, which I talked about, or they can be uptaken and immobilized in organic matter. So it's a very simple process, but it's to keep in mind what happens to the nutrients in soil solution. If the nutrients are not in soil solution, we're not interested. Once they're in soil solution, one of three things can happen. They're taken up by plants, they react with the soil surface, backwards and forwards, or they leach. So if you're talking to a politician, if you're talking to a farmer, if you're talking to a bank manager and you're talking about nutrients, tell them that's what happens to the fertilizer that we put into the soil. One of three things. We want that, we don't want that, so we need to understand this. Because we want them to be taken up by the soil so they can come back with time. Okay, so first take-home message. Three things that happen. Uptake, reaction, or leaching. And soil science is actually understanding this. Understanding how they react with the soil surface, soil solution. Okay, so what this brings us to is starting to understand why they react. What is it about clay? I've said soil solution. I've said clay. That's the most important part of what we're dealing with. Particle size. We're talking about clay being small. Now that can be clay silicates, but it can also be organic matter because that's in the clay size fraction. And it can also be things like hydrous oxide, iron hydrous oxide, rust, clay fraction. This is why it's so important. Because what I've got here is I'm looking at sand, silt, and clay. Those diameters are the same as I mentioned before. But now what I'm doing is I'm giving you the calculation of the surface area. So if we could isolate a gram of sand, so let's say we could get an exact gram of sand particles with an average diameter of 2 millimeters, and we could count or measure the surface area on every one of the sand particles in our gram, we would come up with a number of 11.5 square centimeters of surface area. So 11.5 square centimeters per gram. Now, if we do silt, it's smaller. We can get more silt particles in a gram, and we can measure the surface area. We get a number of 462. Clay, we get a massive number of particles. And what happens there is that our surface area has gone up to 11,000 square centimeters per gram. So the surface area of clay is 1,000 times more than the surface area of sand. That is why, as soil chemists, we're so interested in nutrients in soil solution need something to react with. And what happens is as a particle gets smaller, the surface area goes up. So we're really interested in those clay particles. Now here's sort of like another way to think about that. So this is where I can get some answers from you to break this up. Let's imagine that we've got, now this is not to scale, but let's imagine that that is 10 centimeters and this is full of water. So let's just imagine that we've got on this table a 10 centimeter volumetric flask, and I am able to find a single grain of sand a single grain of silt, and a single grain of clay. Okay, so that's purely hypothetical. I mean, I could possibly get with a pair of tweezers a single grain of sand. It would be very hard to get a single grain of silt. It would be almost impossible to get a single grain of clay. But what I've done is that I've taken my single grain and I've put it onto the top, and I've timed how long it gets to the bottom. So what I'm doing is I'm timing how long it takes for that grain to drop 10 centimeters. So I want some numbers. Let's start with sand. Give me some numbers for time. How long do we think it's going to take that sand grain to drop 10 centimeters? Anybody want to give me a number? Just throw a number out there. Don't be scared. Don't be right or wrong. What's a number? It's going to go pretty quick. So give me a number. Anybody? It'll be fast. So give me a number. Just give me a number. Start the ball rolling. 10 seconds. Cool. 10 seconds. Anybody else? We're happy with 10 seconds? Want to go 1 hour? Okay. No, that's all right. Doesn't matter. So we've got 10 seconds. Okay, so that's cool. So we've got sort of range there. All right, so it's taken that sand particle to go that distance. What about a silt particle? How long is a silt particle? Again, it's just a mental exercise. Give me some numbers. What for silt? It's going to go slower, isn't it? Because it's just kind of a bit smaller. It's got a larger surface area. But what do we think? 1 minute? Cool. Anybody else? You know what I'm going to ask next? You might as well start thinking about the next one. Anybody else want to go more than 1 minute? Less than 1 minute? Okay, we'll do a 1 minute. Okay, clay. Well, what's the clay particle going to do? How long is the clay particle going to take? A day? All right, so 1 day. Anybody else? Half a day? Okay, Randy's probably laughing there because I've already told her what the answers are. Okay, so very much a mental exercise, but it gets us thinking. There's no right and wrong answer. So the sand particle, the actual answer is 1 second. All right, so the sand particle is going to take 1 second. Silt particle, we're pretty close. Silt particle is going to take 5 minutes. But, you know, that's because it's actually got a larger surface area. Not a hugely large surface area, but it's got a larger surface area. Clay particle is going to take 860 years. That is surface area. And that surface area is what controls nutrient management. Now, it's very hard to conceptualize how small a clay particle is to a sand particle, but if we start then thinking about that surface and watching it float down to the bottom of that water because of that massive surface interacting with water's tension, 860 years really starts to put it into perspective. Okay, so a useful little exercise just to start us thinking about how different clay is to sand. Now, this is where it comes to pedogenesis. As soils age and as soils weather, we get more clay particles. And those clay particles come from the breakdown of the sand and the silt, but they also form through the secondary formation of minerals. And that soil on the left there is a photo I took a number of years ago in Mexico. That soil is dark rust. It is just iron oxide. It is very old. It is very leached There is very limited calcium, magnesium, potassium. It is full of iron and manganese hydroxide. And if we look around the world where we see very old soils, that's what they look like. They are leached, they're basically rust. Now, the contrast on the right there is a young New Zealand volcanic soil. It's only several million years old. They're quite similar to many of the soils you have here. It is not leached. It is full of most of our nutrients. It is relatively low in iron. It is relatively low in manganese. It is developing organic matter, and it's rich in sulfur. So how we manage and how we use that soil will be fundamentally different, because it is a fundamentally different soil. It will not have the same clay size fractions because it has not been subject to weathering for that length of time. So we need to think about this, think about the formation of soil in the context of how we use our soils. Now, the other key part, okay, so what I've been talking about there is I've actually got to two of the three most important parts of the soil from a chemistry point of view. What's accounting for this? We've talked about silicate minerals, clay-sized silicate minerals. I've mentioned rust, iron and aluminium, and manganese hydroxides. They are surfaces with large surface areas that nutrients will be retained onto. The other one is organic matter. And we all know how important organic matter is. Okay, it's stuff that's died, it's rotted. Organic material is living matter, it's plant matter that has died, it's rotted, and it starts to turn into ammonia as ammonium ions, and those ammonium ions can be converted to nitrate. Okay, we get NH2 groups that convert to NH4+, which convert to NO3-, which are then hopefully taken up by plants. Now, organic matter is actually an area of huge international research. So right now, globally, models for what organic matter is are changing. And so I think if we're going to be responsible nutrient managers, we've really got to refocus on what organic matter is. It used to be, this is probably what Part Echo was taught, that organic matter was stable. It was the final product of decomposition. We had words like humus, which we inferred was stable, complex, almost perpetual material in soil. That is now not considered to be true. Okay? We now think that organic matter is a continuum. Okay, it's a continuum of constantly decomposing organic compounds that's come from plants, it's come from microorganisms. And what happens is that organic matter is constantly getting smaller and smaller and smaller until eventually it turns into carbon dioxide. Now, some of our soils do a good job at protecting organic matter, and that's where we build up organic matter in soils. And we protect it from microorganisms. But essentially, organic matter is constantly evolving. Now, what happens is that these particles get smaller and smaller, and they become in the clay size fraction. They have large surface areas. They're reactive, they're functionalized, and again, we get reactions on them. So a hint for the future for many of you, organic matter is something that we're really starting to realize we need to know more about. And I'm pretty sure that organic matter is a subject which is rich for ongoing research here in Indonesia. Now, this just gives an indication. I've brought this up as one of the new insights into what organic matter looks like these days. And this is some work from a PhD student from Massey who graduated last year. Now we can see that we've got plants, we get leaf litter, we get root exudates at the top there. That is creating a pool of carbon-rich material in the soil. And that pool of carbon-rich material can either be plant-derived on the left-hand side, or it can be microbially derived on the right-hand side. So we can now start to understand that we have two types of organic matter. That which has come from plants, it has a high carbon to nitrogen ratio. We've got lots of it in topsoil, and we say it has low molecular complexity. And that is very different from microbially derived organic matter. That's organic matter that's been taken into, or carbon that's been taken into and processed by microorganisms. And that has a low carbon to nitrogen ratio. It's got more nitrogen. It has huge complexity. And it's actually what we find in the subsoil. So there is this great insight going on into what's actually happening with carbon in our soil systems. Let me come up. Here we go. And there's another image. All right. So what we're starting off is sort of thinking here about the pathway. Tissues and microorganisms. There's the parent material for carbon on the left-hand top side. We get biopolymers. We get intermediate carbon content compounds, so carbon chains, monomers, and eventually it gets released to carbon dioxide. That's what happens when carbon rots. It breaks down completely, and that carbon will turn into carbon dioxide. But those biopolymers, those intermediates, those monomers go into soil solution. And once they're in soil solution, we get really interesting reactions. We've got on the left-hand side there, we've got the intermediaries linking iron oxides with aluminium. It's the glue that holds together clay minerals. Here in our soils of Indonesia, we get reactions with allophane in volcanic soils. So we get this organic matter that is creating functional complexity and driving what happens with our soil. So it's an area that is ripe for research. Okay, but it's critical to this reaction with the soil surface, that surface being organic matter, as well as clay silicates and our iron and aluminium hydroxide. They're all there. Iron oxides, clay minerals, organic matter. Those are what is accounting for this reaction in the soil. Okay, so there we go. Soil solution. We now know what we're reacting with. The next part is why. Why are we getting this reaction? Now, the key sort of message here is that we get reaction because those surfaces, those clay surfaces, are charged and they have negative charge. Sure, we've had concepts like point of zero net charge. There is a relationship between the surface and our wider environment that means that those surfaces have negative charge. And there are two mechanisms. One, don't have to go into the detail, but we call this permanent charge, isomorphous substitution. It's all about how the rocks formed. As rocks form, we get substitutions. Commonly, aluminium substitutes for silicon, and we get charge in our rocks. And when the rocks break down to form soil, that charge passes through to the soil. So our clay minerals, our clay silicates that are in a solid phase have charge, and that charge comes from isomorphous substitution. The other one is more interesting. I'm just going to flip this over. And this is again where organic matter comes into its own. Okay, so what we know is that we also have another type of charge in soil called variable charge. And what this is, I might actually go to the next slide, is all about the reaction of our surfaces. And if we start thinking about those complex organic matter surfaces, it is the reaction of those surfaces with our pH, with the acidity of our environment. Oh, I'll come back to that. Okay, I'll just do isomorphous substitution first. So we've got two. We've got permanent charge, which is from our rocks, and we've got variable charge, which is on organic matter. Now, if we look at our rocks, this is kind of what happens. So I mentioned there that isomorphous substitution. Now, this is an example of a rock with a silicon structure. And those blue dots are silicon atoms. The red dots are oxygen. So we've got quartz, or we've got a basic rock that makes up most of the earth. But every so often, what happens is that we lose one of those silicons and we put in an aluminium. Now, silicon wants to have a bonding. Silicon in our chemical structures is Si4+. Aluminium is aluminium 3+. So if in our rock here, we knock out that blue silicon and we put an aluminium in, and that's what happens in geological systems, all of a sudden, we've got an imbalance. Now, the rock can't change that. It has to live with it. We get an imbalance and we get a negative charge. So by having that substitution, we have a negative charge. And the only way to account for that charge is for that rock to pick up a countercation. And in that case, we pick up potassium. Now, this is what happens in the earth. This is what happens as rocks form. And if we've now got a rock that has a negative charge and it has potassium in it, and then that rock breaks down and makes our soil, we get that negative charge in our soil, and we get the potassium in our soil. And in fact, the picture I was looking for, this is actually how many of our rocks form. On the left-hand side there, we've got quartz, the most simple, the most basic type of rock. It is just silicon dioxide. But if we knock out some silicon and we put aluminium in, and then to counter that charge, the rock picks up potassium, we get that rock on the bottom right, a potassium feldspar. If it picks up sodium as opposed to potassium, we get the rock on the top. We get a sodium feldspar. And that's actually how rocks start to form. The key thing there is the charge passes into the soil. As the soil breaks down, as the rock breaks down and forms the soil, that charge passes through. Okay, now the other one, and this gets back to organic matter, which is where I wanted to be. So this then comes into organic matter. Right? So the first one, isomorphous substitution, permanent charge. There's nothing we can do about it. We just have to live with it. Organic matter is more complex. Now, this is actually an electron microscope image of biochar. And I'm sure that's something that some of you have had some experience with. And I choose this because it's a more stable form of carbon. Inside 50 micrometers. And what I've done is I've blown up that ring and I've done tapping. And the particular element or the particular functional group that we're most interested in is the one on the left-hand side, that carboxyl group. So carboxyl groups are really common in our organic matter systems. And what a carboxyl group looks like is this. So imagine that this is a surface, a soil surface. And then sticking off the soil surface, we've got a carboxyl group. Now, what happens is that this is an acid. And we all know a little bit about acids. What happens is that this, we can lose. We can actually take away that acid, so the pH goes up. pH increases, we remove acid from the system. And what actually happens is that that carboxyl group becomes negatively charged. We can go the other way. We can add acid, so we can get more acidic. And what happens here is our carboxyl group actually can pick up a second H and it becomes positively charged. Now we call that variable charge. So if we've got organic matter and we have an alkaline environment, we lose the H+, that organic matter surface has a negative charge. If we have an acidic environment, we can add H+ onto that carboxyl group and we end up with a positive charge. What actually happens in our soil systems is that we are here. The pH of our environment is such that our variable charge is negatively charged, and that then accounts for what's happening on our surfaces. So you would have all come across the values or concepts of cation exchange capacity. Okay, humus, organic matter, really high cation exchange capacity, has lots of negative charge. Clay minerals have variable charge in the sense that they've got variable levels of cation exchange capacity. Just depends on the makeup of those minerals as to what charge they express. So we've got our soil solution. We want it to go into the plants. We don't want it to leach. We're looking for it to react with the soil surface. So what we now find is it's reacting with the soil surface because the soil surface has a negative charge. Cations are retained, anions are repelled. And that is actually why nitrate leaches. It's negatively charged. It's in the soil solution. It can't bond onto the soil surface, so it has no choice but to leach. And it's a critical concept to remember if we're trying to look at sustainable nutrient management. It's not the farmer's fault, it's actually the soil's fault. So we have to work around the soil to make sure we know what we're doing. So what this means is that the soils hold on to nutrients. And the electrostatic, this charge, this attraction of positive ions in soil solution onto the negative charge of the soil surface is our primary driver of nutrient exchange. And we call that non-specific adsorption. Right? It's a simple electrostatic attraction. Okay, anions are attracted onto positive soil surfaces. Cations are attracted onto negative soil surfaces. We know that all of our cations are retained on the soil because the soil is dominantly negative charge. So we don't talk about them. We don't really consider cation leaching because they stick to the soil. What we talk about is anion leaching because we now know that they can't stick to the soil. So when we start thinking about our anions, we need to be considering that mechanism by which they can be absorbed. Nitrate can't be. Chloride can't be. Sulfate really struggles, and that explains why nitrate leaches. It doesn't explain why phosphate leaches. Okay, so we've got something else that we've got to use there. Now, non-specific adsorption, it's reversible. It's controlled by soil factors that dictate variable charge. pH is important. We have concepts like point of zero net charge. But essentially, we don't see anions retained, we see cations retained, and it's an overriding rule of nutrient chemistry. We do have one other option, and that is what we call specific adsorption. Now, specific adsorption is a little bit different. And the example I want to give you for specific adsorption is of hydrous oxide, aluminium and iron hydrous oxides. So let's pretend we've got some rust in our soil. And this is what it looks like. All right, so we've got a soil surface. Sticking off that soil surface, we've got some iron, some hydrolyzed iron hydrous oxide. Now, in fact, the hydrous oxide has no charge. There's an extra hydrogen there, but it's a bridged hydrogen, so that hydrous oxide has no charge. So if we had calcium come along, calcium would say, I've got a positive charge. The hydrous oxide's got no charge. Calcium's not going to react. Calcium's not going to be interested. It'll go and find a negative soil charge. Nitrate will come along. Nitrate says, right, I'm negatively charged. Hydrous oxide's got no charge. Nothing's going to happen. So nitrate disappears. And so we carry on. Potassium, chloride, bromide, sodium. So we carry on until we get to phosphorus. Now, the first rule is the electrostatic. Phosphorus, dihydrogen phosphate, is negatively charged. Sees that the hydrous oxide's got no charge. There's no interest. But phosphate has one other option. Once it's worked out it's got no electrostatic charge, it can actually say to itself, hang on, I can form a covalent bond. And that is a unique relationship between the phosphate and this group. And what actually happens is that we end up with a new structure that looks like, that looks like this. Okay, what actually happens in this case is that the phosphorus covalently and hydrous oxide, and it becomes part of the soil. And we call that specific adsorption. And it's really what drives your phosphorus nutrition here in your volcanic soils of Indonesia. Now, what this does is it works for phosphorus, it works for molybdenum through the molybdate ion, and it works for selenite. So it's not just phosphorus, there are a couple more, but it's really important in managing our nutrient flows. All elements will consider electrostatics, but it's only the cations that stick around. Phosphorus has another option, and that's why calcium will be stick to the soil, why nitrate will leach from the soil, but why phosphorus will actually stick to the soil and can be lost through erosion. Now, if we look at what's happening there, we can see that our non-specific adsorption, and we can compare that to our specific adsorption. Non-specific adsorption, nitrate chloride. Specific works for phosphate selenate. And the key ones at the bottom are that non-specific is weak. It's an attraction. Specific adsorption is strong. Okay, so we can think about one being reversible, and we can think about one being non-reversible. There's your homework done. Explains why nitrate leaches, but by why phosphate will run off and will erode. Now, what happens is that we get a soil particle. There's our silt particle, provides structure, provides physical structure. What happens is that we get iron and aluminium hydrous oxide. It weathers out of our soil. It covers our silt particle. It creates a place to take phosphorus. So phosphorus gets stuck onto our soil particles. We get more iron that erodes, more iron weathers. It coats that phosphorus and creates a new layer for more phosphorus to stick onto. So again, it's a dynamic process. And that's where we start to talk about different forms of phosphorus in soil, Olsen phosphorus versus non-Olsen phosphorus. So we can start to explain our nutrient management. We can explain some of the terminology we use by considering what that reaction on the soil is. So what does this mean? All right, before we pull this together and think about rice. So what are the implications here? We go back and we think about what we've covered. Oops, probably gone too far. And we think about, oh, hang on. Go to the next one. Going very slow. There we go. Okay. We'll get there eventually. And the next one, there we go. Are they controlling it on me? So if we think about what that means, here's the take-home message from understanding nutrients in soil solution, uptake in plants, avoiding the leaching, what's happening with our soil surface, the time, the frequency, and where we put our fertilizer is essential to increasing our efficiency and removing the risk of environmental contamination. So for nitrogen, it's mobile. Nitrogen moves in the system. It's soluble. So where we put it is not important, but when we put it and how often we put it is. So for nitrogen, you've got to be really careful about when and where you use it. You do not want to use it before a big storm. You'll lose it. It'll be gone. Whereas phosphorus is the complete opposite. If you're growing a crop of bok choy, you do not want your phosphorus on the surface. You want your phosphorus in the soil. If you're growing maize, you want your phosphorus in the root zone because it will not move. It'll get stolen by your soil. So you want it in a place where the roots can use it. So we can understand that based on those reactions with the soil surface. So when we use fertilizers, how often we use fertilizers, and where we put them becomes critically important. Because what we're trying to do is avoid that. We have this in New Zealand. Our systems are phosphorus limited. We have lots of nitrogen in our water. And when we lose phosphorus from runoff, that's the result. Even in New Zealand, we end up with eutrophic water. That is an environmental challenge. You all are developing the skills to minimize the risk of that happening, to protect your water. Okay, so what I want to do is that, because that's my theory, and it's actually good timing, because Rennie told me I had about an hour, so I've got about 10 minutes. I want to now say, okay, provided the framework, let's think about the environmental challenges of rice. Let's think about the environmental challenges of farming, and how can we use this knowledge to actually manage our environment and to ensure that our integrated systems are sustainable. So I found this story on the internet. How can we grow more climate-friendly rice? It's a big problem. I chose rice because you grow a lot of rice here in Indonesia, and we recognize today that rice is a major environmental and a sustainability challenge. Now, just a couple of key facts, right? Globally, paddy rice is responsible for up to 50% of global cropland methane emissions. Now, we're really worried about emissions from soil, and what we find is that paddy rice is responsible for about 50%. It's also a major source of nitrous oxide, a greenhouse gas that's even worse than methane. And we also recognize that surface runoff from our paddy fields is a significant source of diffuse pollution. So it's an essential part of your economy, but also globally, it's a major environmental challenge, especially as we understand our environmental systems. Nitrogen cycles. Okay, I'm hoping you've all got a level of understanding. I'm not going through the nitrogen cycle, but what we do recognize is that nitrogen cycles. We get organic matter. Now in New Zealand, we're really worried about dairy cattle. So there's a cow, less important here. But if we think about the nitrogen cycle, we have organic matter. It cycles into NH4, it converts to NO3-, and we hope it goes back into the plant. But under paddy fields, we can actually get that nitrate converting to nitrous oxide. So if we think about this reaction, and we're talking about paddy fields, we've got to think about all of the reactions. What happens when it reacts with surfaces, and how it engages with microorganisms, and how it engages with organic matter. The nitrogen cycle is critically important here. Now, water quality happens at a number of scales. And in New Zealand, we use a lot of modeling. So we use modeling systems and modeling packages that try to understand our sources of emission of nitrogen and phosphorus, and how we can actually track those nitrogen and phosphorus systems through our environmental pathways. So when we apply this knowledge to our farming systems, we've got to take a step back. And modeling is a key way to achieve an outcome. We do a lot of modeling that tries to understand where the nitrogen and phosphorus is going. And a lot of it we see as lost from the root zone. Okay, we have cities that will release nutrients into waterways. Our crops will release nutrients into underground waterways. Septic tanks and effluent disposal will release nutrients into underground waterways. The question marks are really important because the question marks there indicate the aspects that we don't know about. Now, we do a lot of work at Massey, and perhaps this is something for future collaboration with UB. We do a lot of work looking at what happens beneath the root zone. So we do a lot of work with suction cup, with piezometers, to understand what is going on with that nitrogen, not the phosphorus, because remember it doesn't leach, what is happening with the nitrogen beneath the root zone. And that's where the modeling comes in. So we can install piezometers, we can install suction cups that can actually establish the amount of nitrogen that's escaping, that's not reacting, it's not taken up by plants and is leaching. Because we're trying to protect those underground waterways. And what a lot of our work focuses on nitrate or nitrogen attenuation. If we can understand that system, And we can, oh, no, I'm going to stop playing with that. It's going to break. If we can understand that nitrogen attenuation, we can actually model that nitrate. Remember, nitrate's our key concern. It's going down the system. But what we're starting to understand with science is that it doesn't go down the soil profile the same in all our soil environments. Sometimes nitrate can actually convert to nitrogen gas. And this is a real big advance for science. If we can actually take that nitrate and we can convert it back into nitrogen gas, then that will go back in the atmosphere with no environmental impact. So nitrogen attenuation is becoming a huge area of globally important science. And we have coefficients that are linked to hydrogeological conditions that allow us to model how much nitrogen our soils can attenuate. So how much of that nitrate can our soils convert into something that is more safe? The problem is nitrous oxide comes back, because nitrous oxide is an intermediate step in that reaction. Now, what we do here is we've got to bring in microbiology. I told you this is where the chemistry starts to be applied. But this is the area for the future. I'm trying to challenge some of you to think about this in your future studies. We get the redox ladder. We know that we've got aerobic and anaerobic conditions. Okay, we start off with oxygen, and eventually we convert down, we reduce the system to hydrogen gas. And we see that there are steps in the redox system, which is bringing in chemistry, it's bringing in microbiology. And we need to use that knowledge of redox chemistry to follow our attenuation pathway. So if we pull this work together, what happens is that we can use nitrate attenuation to map our land. We can classify land based on its ability to protect the environment, or we can classify land to assess its vulnerability to degrading the environment. And I think, again, this is an area where Indonesia could benefit from your scientific input. Now, these maps are an example from Ireland. I would love to see these sort of maps in Indonesia. What these are is pollutant impact potential maps, based again on an understanding of uptake, reaction, and leaching. And what these lands do is that they have darker color. This is the whole of the country of Ireland, and the dark colors is where we've got more risk of creating pollution through farming our land. So we can use our knowledge of the chemistry, we can use our knowledge of the modeling, we can use our skills to be much more clever with how we use our land to grow food. Now in New Zealand, we've done similar. What we can do is that we can look at land and we can say that some land has a great capacity to reduce nitrogen loads. So we can choose land and we can safely apply nitrogen to it, knowing that that land will attenuate the nitrogen, it will not leach the nitrate, and will actually convert that nitrate into nitrogen gas. So that green land, we should farm it. That's where we could grow it. If we could grow rice in New Zealand, that's where we would grow rice. Whereas that other land, that red land, we do not want to be putting nitrogen on it. It's leaky. The nitrate will go through the profile and it will end up in the water. So we can apply this understanding to map our landscapes to increase our ability to integrate our nutrient management. So what are we going to do? What's our solution? So here's your research. I'm hoping some of you could pick this up. If we think about nutrient management in rice paddy fields based on the science I've explained, based on the opportunities I've been talking about, the solution lies in water management, inorganic inputs, and different cultivars. We need that integration of soil science and plant science. Now, here's a comment on the right that I found fascinating. There's a lot of commentary now saying that flooding isn't always necessary to grow rice. Instead, we flood paddy fields because it stops weeds growing. So there's a change in this perception about how we even grow rice. Now, the biggest problem we've found is that you can dry your paddy field out periodically. The trouble is then you start generating nitrous oxide. So when the paddy field is flooded, you generate methane. When your paddy field is dry, you generate nitrous oxide. So you can't actually win. The secret is that water management. And there are guidelines to say that the fluctuation should be between 5 centimeters above the soil profile to 5 centimeters below, not depth of water to completely drain. So water management, keeping in mind our nutrient cycling, is perhaps the key to more sustainable production in the future. So for nitrogen, water use is a major issue. Too much water use, you get methane. Too little water, you get nitrous oxide. So you can actually change that with good practice. Now for phosphorus, we can stop the erosion, we can stop that loss from runoff through ditches and ponds. And that's why farmers have ditches, detention bunds, ponding that recycle that water and the nitrogen and the phosphorus back onto our crops. So we can integrate this knowledge, do a better job. Now, nitrogen fertilizer actually increases carbon utilization. So in fact, we can see that with nitrogen fertilizer, we can reduce methane emissions. The trouble is if we have the wrong water level, we can increase methane emissions. So it's integrated. Water and nutrients is integrated. We have anaerobic microorganisms that actually will oxidize methane through reduction of nitrate. So the microbiology comes in, links to those nutrients to come up with a sustainable system. Trouble is though, if you add too much nitrogen, you increase the risk of nitrous oxide loss. So again, you've got to look at the big picture and it's integrated towards a solution. Now here's a paddy field from Sumbawa, okay? And here's sort of like the key things that we can do. And here's a challenge for some research projects. So I thought I'd finish off by putting some research projects out there that you potentially could work on in the future. We know that ammonium-based fertilizers are less likely to leach. Ammonia ions are stuck to the soil. So maybe we could inhibit methane emission by better use of nitrogen fertilizers. Now, another thing is that iron 3 enhances iron-reducing bacteria, which inhibits the methane-generating methanogenesis reaction. Iron 3 amendment of soil can actually reduce methane emissions by 50%. That's potentially a really good area for research here around Central Java. Amending iron 3 into soil to look at how we can change the microbiology and change the nutrient profile, area to go. And similarly, we could actually look at overcoming iron deficiency. Because there's one project that I heard of about 10 years ago, Echo, here in Malang, that I've still never done, and that was the local paddy rice. Do you remember the story of the indigenous paddy rice that was making people feel more full, that had making them feel more healthy, and it was in high demand from old people's homes and hospitals? So I think there's a huge opportunity to bring in cultivars and rice with nutrient management around climate change here in Indonesia. So there's some really cool opportunities for future research. So what are my take-home points? Here's my last message. If we want to think about it, and it goes back to my challenge to talk about integration. So consideration of soil and water must be integrated in our approach to fertility management. First challenge we've got is to improve water use efficiency. So we need to consider spatial variability. We need to match soils to water application. Right? We have to think about what is the water application rate we need to use based on the properties of our soil. What is on the soil surface? What is controlling the reaction? And what is the water going to do to that soil? So there's the first point. We've got to match soils with water application rate. And then the second part is that we've got to be targeted and effective. So different settings, different hydrogeological settings will affect leaching and runoff of nutrients from farms to receiving waters. So we've got to be targeted and we've got to be effective. And the fundamentals of soil chemistry that I've spent most of this lecture talking about are critical to doing this. You've got to have an understanding of this to be able to do this. You need that backbone of understanding to be able to achieve sustainable agricultural production. And there's my challenge to you for this semester. Anchor your base science around your solution. So what could you do next? Well, bring this into your research projects. Contaminants, pollutants, yield mechanisms, they are all integrated into sustainable nutrient management. Explore nutrient superior crops. I really would like to see some work around indigenous paddy rice. Really what you're looking at is high value, sustainable farming system. And your science that you're doing will actually allow you to drive food security and agricultural development here in Indonesia. And I look forward to seeing how we can support that way forward. So this photo is where it started. This photo here is back in early 2010. You can see a very young Professor Eko on the right-hand side. There is a very young Professor Wani Utomo in the middle there. The chap on the left-hand side is now Rector Unram, and there's a very young-looking Dewi Krishnayanti there on the left too. So that's where it started. You were not there. You were quite young then, Rennie, but that's where it started. So ngā mihi, mā te wā, as we would say in New Zealand, and thank you for listening.
Thank you very much. Please give a round of applause. Thank you very much, Professor Christopher Anderson, for the sharing, for broadening our view in soil fertility management. And for all the students joining us online or offline, please feel free to ask your question. Now we are on discussion session. We have like 20 or 15 minutes to have a discussion session. Please raise your hand and ask your question. Maybe the committee please help for moving the microphone for students that want to ask question. Our student like shy when actually they want to ask. Oh, it's the same Indonesian and New Zealand student. Okay, student, please don't be shy.
Ask in Bahasa.
Yeah, you can ask in Bahasa. I'm happy to help you like as a facilitator to translate your question. And we have many lecturers here that also help you for translating when I couldn't translate your question. Or maybe for the Honorable, our lecturer here, Prof. Kurniatun, Pak Budi. Oh, okay, for student first. See, you have like a good chance to ask question. This is like good chance for you, like a meeting lecturer from overseas, from Messi University. This is like a rare chance that you hardly can find this chance to ask directly about soil fertility management. Or maybe, can I have question?
You certainly can, Renee.
Thank you for the chance. Chris, this your talk about the soil fertility management in paddy field. As we know, Indonesian, our staple food is paddy, actually rice. And you told us like we couldn't stop planting paddy because this is our staple foods. But we need to manage like the water use efficiency and many more, like applying microbiology for nitrogen attenuation. But in Indonesia, like we have from Sabang to Merauke with different climates. So what is your suggestion for us in managing this soil fertility management that has less damage for the environment, but with still has high productivity? Thank you.
I think, Renee, that's not just a challenge for Indonesia. I think we find globally that we just use too much nutrient. We use more nutrients than we need because we think that by adding more nitrogen, we're going to get a better yield. And so it comes back down to good science and evidence to actually diagnose what is the nutrient requirement given the capacity of land. Now, all this information about nitrate attenuation and attenuation factors, this is cutting edge science. And what I'm doing is I'm giving you the challenge to say this is something that UBI could be looking at engaging with. And being able to actually look at land and then assess the likely risk of losing nitrogen would allow you then to be much more clever about how you grow crops. So we need nitrogen, but if we are managing our nutrients and we're managing our water, knowing what the challenge is and what the outcome is, then you're going to get your yield at minimum environmental impact.
Thank you for the response. Student, please ask your question. We have time like 15 minutes. This is like a good chance for you. Or maybe.
Oh, it's a question. Okay.
Oh,
Yep.
yeah. We have question from student that joining us online from Zoom meeting.
Yep.
Oh, this is in Bahasa Indonesia.
That is good. You'll have to translate for me though.
Let me try. Okay, I will try to translate, but this is like the only summarize for the question.
Yes.
The student saw your slide about young volcanic ash in New Zealand, and he or she, I have no idea no name there, like she. Oh, yeah, Alice. Alice is a girl's name.
Yep.
And she said that this good for like growing vegetables, crops. However, the young volcanic is like less fertile. So how to make that young volcanic as fertile as maybe more developed soil?
And well, that's been a big challenge in New Zealand because because of our young soils, we are very deficient in phosphorus. So the only way that New Zealand has been able to overcome that is through quite extensive application of phosphorus to land. It's got the base cations, it has sulfur. The allophane, the volcanic mineral, preserves organic matter. So we've actually got good organic matter buildup. The cation exchange capacity is okay. The limiting factor has been phosphorus. So New Zealand has had to apply considerable amounts of phosphorus through top dressing to be able to bring that land into production. But it's a
Okay,
good question.
Alice, for the second question, question number 2, for the silica element quartz, it's like good for paddy. However, it's like difficult to uptake quartz and make it available for plants. So is there any option to make quartz available for paddy, especially for paddy?
Okay, so what that question's talking about silicon deficiency in rice plants.
Yeah.
Yeah. So one of the issues with silicon is that it is also an element that will specifically adsorb onto. It's one of the several elements that will specifically adsorb onto mineral components in the soil. And that is a challenge to allow enough silicon to be in soil solution for uptake. If you are in a situation where you don't have silicon, really the options are to go through your blended fertilizers to actually have silicon in a fertilizer product that's going to provide it, or look at changing where you're growing. And I think what we're starting to see globally is that if we take paddy rice and then we take it out of paddy rice production and put it into dryland cropping for a period of time, that often will replenish the pool of available silicon before it goes back into paddy rice. So it's a rotational system, recognizing the limitations of nutrients in the soil.
Oh, like returning the biomass to the soil.
Yep, and that we're not necessarily burning it as well. So actually coming back in from an organic cycle. But if you take your paddy rice out and actually let it dry and crop it for a period of years in dry land before it goes back into paddy rice, that can reinstate the equilibrium.
Oh, yeah.
But that is research. That is, that's the sorts of research project that need to be driven to get data that works for this area of Indonesia. We don't have paddy rice in New Zealand, so it's not an area I have a huge amount of expertise in, but silicon deficiency is becoming more talked about.
Yeah.
Good questions. Thank you.
Thank you for the question, Alice Sofiati. Any question from the student that joining us online or student that joining us in this hall?
I've got a question for the students. So put your hands up if you are studying soil science. So students studying soil science, I'm just curious to know who we are.
We have many here.
So hands up, soil science students.
I'm also studying soil science here.
How about plant science? How many of you are doing plant science?
Plant science, please raise your hand. You are like a postgrad student. Please don't be shy. You are from
one hand.
Only one hand.
Yeah.
True.
Yeah. So a lot of you are doing a bit of everything. You do plant science and soil science, which is good.
Any question again? Oh yeah. Committee, please give the mic. Oh. Feel free, Prof. Eko. Please say your name and your department.
Sebelumnya, Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Nama saya Azizatul Fajriya dari program studi PTA atau pengelolaan tanah dan air. Di sini saya izin menanyakan terkait dengan label soil carbon. Nah, itu mungkin bisa dijelaskan kembali karena saya masih belum terlalu paham terkait dengan mekanismenya.
Soil carbon and
Soil carbon pool.
pool.
Yeah.
Yeah. Okay. That's it?
Yeah.
Okay. Your name? Aziza. Chris, Aziza asked about soil carbon pool. She wants to have more view on soil carbon pool.
Yep.
Yes.
Okay. In what context are we? Because I mean, there's a lot of work now that can be done to extract soil carbon and then fractionate it, put it through mass spectroscopy to look at the carbon size. But you've also got to remember that in certain soils, carbon will be preserved in soil structures. So what we see is that carbon will be metabolized by microorganisms. That's what happens. Carbon is processed by microorganisms, but in places it can be protected. And if you want to quantify your carbon, you've got to extract it and then actually map it or use spectroscopy, mass spectroscopy, to look at the relative carbon fragments. Now, there's good methodology. I mean, I can share the papers that I've cited with you, but it's analytical chemistry to really see what those carbon fractions are and to then start thinking about whether they've come from a microbial pathway or whether they're just fragments of plant-derived carbon. Okay, so the carbon-nitrogen ratio is important, and then their functional complexity is important. But I'm happy to share the literature so that we can explore what you're actually needing. Really important. That's where you're going with your research, to understand what your carbon is, and that will tell you how long it's likely to stay around for. That is really important to managing nutrients, but also to reducing our greenhouse gas emissions.
Yeah, that's
so good,
really
Aziza. Good.
Any feedback from Aziza? You want us more? Ogi Orona? Okay. Please give the microphone.
Yeah, thank you very much for this opportunity. Thank you very much, Professor Chris, for this lecture. I want to ask you, as I know, if the phosphate can make strong bond in Fa and Al, but this lecture tell us about the function of organic matter can dissolve this bond, and how much significantly organic matter with the microorganism function to release the strong bond, and if this phosphate reaction with organic matter and microorganism, there is any potential to leaching or just the erosion for reduced in soil. Thank you very much.
Okay, no, it's a really good question, and it's exploring a number of integrated areas of science. So what breaks that strong bond is microorganisms. Okay, so when we see water pollution, it's because that strong bond with phosphorus has gone into water and microorganisms have broken the bond and released the phosphorus back into the water column. Now, if you've got high microbial activity in soil and you can stimulate that microbial activity, they will break that bond, and the hope is that the plants will take it up. I don't think we'll get phosphorus leaching, because what will happen is that the phosphorus will move down the profile into an area where there is less microbial activity, and it will reform and it will rebind a strong bond. So it's just kind of a vertical movement. So it's leached out of the topsoil into the subsoil. It won't necessarily leach into groundwater, which is why we don't see phosphate leaching into groundwater. We only see particulate phosphate in water. So microorganisms are key. And so you can stimulate increased phosphorus cycling by stimulating microbial activity. And that's another really big area of science now, to manage your microbial population to actually increase your cycling of phosphorus in the system. So in New Zealand, we really struggle. It goes back to Elisa's question in the New Zealand soils. Because our soils are young and they're not particularly microbially active, phosphorus gets stolen and there's no way to get it back. But if your soils are more aged and they've got more functional diversity, then you can cycle your phosphorus better. So the way to solve it is to understand your microbiology. Now, with DNA technology, and Reni's been involved with some of this with the work she's done with mercury, but with DNA technology now, we can look for microorganisms. So instead of trying to leach phosphorus out with acid, stimulate microbial activity, and that could actually be just as good a fertilizer as adding more phosphorus. So that biology is so important now. Good, thank you.
Yeah, we have other question. Mas, please.
Perkenalkan, nama saya Strian dari agronomi. Tadi sekilas dijelaskan mengenai manajemen nutrien yang katanya semakin kecil partikel dan semakin luas permukaan tanah itu bagus untuk manajemen nutrien serta bagus untuk cadangan nutrien. Selain itu juga adanya substansi organik juga bagus untuk cadangan nutrien. Nah, pertanyaan saya, teknologi apa yang digunakan negara-negara Timur Tengah dan Israel hingga menjadikan pertaniannya maju? Padahal notabene mereka hanya memiliki gurun yang partikel tanahnya itu besar-besar, luas permukaannya kecil, serta mudah mengalami leaching. Terima kasih.
Okay, thank you for the question. I will try to translate your question. So he asked about, you said that the smaller particle, it holds nutrient better than the bigger particle. And it, how does it hold the nutrient longer than the bigger particle. So this is like good for soil fertility management. For example, like in Israel or Middle East countries, their agriculture, like they have good agriculture management because as we know, the soil there like big particle sands that the holding capacity of nutrients like poor than the smaller. So he asked about how to manage the soil fertility or how soil fertility management over there to increase or to support the production of agriculture crops. Yes. Thank you, Bujo.
So when you're dealing with a sandy soil, basically you're running a hydroponic system. And this is a big challenge, again, globally in areas where they've got very, very free draining soils with no clay and no organic matter, is that you're having to put nutrients in continuously to satisfy the nutrient demand of plants, but you run a big risk of leaching it. Best example I can give you that you probably not thought of is the United States. So large parts of Washington state in the United States where they grow extensive amounts of wheat, what they're basically doing is pumping nitrogen in, it's going into the rivers, and they're just basically pumping the rivers back onto the land. So they don't need to be adding more nitrogen because there's so much nitrogen that's just going through the system. In New Zealand, we do it the complete opposite because we try and build up our soils, build up organic matter. We're lucky we have clay silicates and we have hydrous oxide so that we don't have to add fertilizer the whole time. Because you want to put fertilizer in, it's taken up by the plant, and you want everything else to then go onto the soil surface. And then what happens is that once the concentration drops in the soil solution, comes back into soil solution. You put more fertilizer in, you push it back onto the soil surface. So that's what this part of the reaction is. There's no opportunity to go onto the soil surface because the cation exchange capacity is so low. You're just going to have to cycle it round. So Israel, in areas where they're growing plants in the desert, they have to add continuously soluble nutrients, which is fine if you can trap the leachate, but it's very dangerous if you can't. So understanding the basic science will allow you to make better decisions on that.
Okay. Any feedback? Yeah, that's all. Still, the committee, we are running out of time, right? Yeah. Oh, yeah. Please. Yeah, it's possible. Mas Afif, please. The microphone. Oh.
Yeah. It might be turned off.
So I'm looking at the file.
Yeah.
Now, it's not very much to our question. I can really put it that the file then since you have a title incorporated not only every form, but also anything on the relationship with the soul. So in the climate change era now, what do you think? That is right. Can we do something with something to do with of selection of the rice quality part? For example, because the increases of the methane, it is related to productivity, good productivity. So, from the economic point of view, maybe we could select what is that variety with a lower productivity to reduce the methane. That is one thing. The second thing, from the again, still getting what interested in one, selection on the high use density, to increase the state of the hydrocarbon phosphorus or nitrogen to reduce the existing or the availability in the soil. That is three. And then the last one, of course, that the last one is inserting, combining, or rotation. That means by and liquid crop. And that means you can reduce usage of nitrogen, fertilizer, chemical application. What do you think about it? Because you are thinking, you can do something how to reduce of the loss. I really appreciate the idea about it. Even there is how to suppress our loss, nutrient loss to the environment. Thank you.
Thank you very much. Look, I think you've nailed the idea of integrated. And I think, going forward, I've hopefully given you a challenge for some of the ideas, and you've picked up on many of them that could underpin research work, integrated research work that could be done within this faculty that combines cultivars with mapping land to identify high and low risk areas, and then match greater root volume in high risk areas with less root volume and low risk. That's the integration. And we've got a platform of scientific knowledge to build on. What is needed is projects that go and do it. And so I think going forward, every single point you've said could form the basis of a really exciting research trial that would generate real data that will help policy decisions. Because what we've got to do is that we've got to get the science into the decision making. And how we use land must be controlled by evidence, not politics or emotion or greed. So here we're talking science. What I'm trying to say is that base it on this platform of basic knowledge. And then the second half of what I've talked about is that, right, where's it going? And I would love to think that we can get some really cool projects that do map out exactly what you've said and test variables. Because I don't have the answer now, but hoping in this room, the students that will actually give us the answers. So I think you've laid some really great challenges for the future. Thank you.
Thank you for the response and question from Bujo. Now we are running out of time, so thank you for Prof. Christopher Anderson for your amazing sharing that broaden our view and knowledge in soil fertility management. And please give round of applause. I have conclusion for this lecture. As a take-home points, soil and water must be integrated in approach to soil fertility management. Water use efficiency, site-specific hydrogeological setting is a fundamental of soil fertility management. I apologize for all my mistakes during guiding this guest lecture. And thank you very much for all students that joining us online and offline. Thank you for all the lecturer that came today, and thank you, Prof. Chris Anderson. And wassalamualaikum warahmatullahi wabarakatuh. Good afternoon,
Oh, wait a minute. All right, wait a minute. Okay, thank you very much for Prof. Chris. And then I would like to inform to the students, so you need to submit your summary of today's lectures to your course lecturer, and do not forget to fill in the attendance list, especially for the online students. And I would like to tell about the assignment, ketentuan tugas for undergraduate students, mahasiswa S1. Please make a resume 1,000 until 1,500 words with Arial fonts 11, 1.5 points, and with the normal margins, and with A4 paper for the online or for the undergraduate students. I will switch to bahasa. Jadi mengumpulkan rangkuman perkuliahan hari ini untuk mahasiswa S1 dengan ketentuan 1.000 hingga 1.500 kata, font Arial 11, spasi 1,5, margin normal dan ukuran kertas A4. While for the graduate or the PhD students, mahasiswa S2, magister and the PhD students, for the task will be depends on your course lectures. So mahasiswa S2 dan S3, ketentuan tugas diberikan kepada dosen pengampu masing-masing. Jadi silahkan ditanyakan kembali kepada dosen pengampunya masing-masing. But for undergraduate students, please submit your task in Google Classroom. Okay, and you can see the today's lecture today in Faculty of Agriculture YouTube. Okay, we have already shared there. And don't forget to fill in the attendance list in Google Form, especially for the online students. All right, so for the next, I would like to, we would like to appreciate Prof. Chris Anderson from Massey University by hand over a souvenir from the graduate program. The souvenir will be handed over by